When the CPU is powered on or a reset signal is received, the PC, the program counter, is always set to 0. It's not the case for every CPU, but for the 8080, 8085 and Z80 it is. So your ROM should always start at the address 0. A quick example: loading the accumulator with 12, incrementing it and stopping the program. So at memory address is the first 2-byte command. 3E stands for MVI A, and 12 at address 1 is the value. And at memory address 2 is the increment A. And at memory address 3 is a halt. So program counter is at address 0, loading the first command. A is loaded and the program counter is 2. That's here the next command, incrementing register A and doing the halt program. To modify the program counter, you can use the command jmp, stands for jump, and you specify a 16-bit address. So at memory address 0, we have the command C3, stands for jump, and you see here the memory, the address is saved in low byte, high byte order. So the low byte is saved first, and then the high byte. C3 and memory address 1 is 40, and memory address 2 it's 0. Program counter is 0. Next command is jump to address 40. And the program counter is set to 40, and the next command is a w.o.p.r instruction. It's no operation. And the hex code is 0. So at address 40 there's a 0. A 0 means the CPU just consumes, I think it's 4 cycles. Yeah, 4 cycles. It's just a placeholder. But don't expect that your memory on your board is always set to 0. It will be filled with random numbers. So at memory address 0040, let's do for fun an operation and jumping back to the halt, that's memory address 3. So here at address 40, that's an operation, and a jump back to 0003. We are at program counter 40, there's an operation instruction, and here we are jumping back to the halt. Luckily, you can use labels. Let's call this label 1. And here we're specifying the label 1 and calling this stop. So the assembler will include the correct address. So label 1 is address 40 and the stop is at address 0003. So this jump is called an unconditional jump. There's no condition needed, he will just jump. There's another one. I'm loading the register HL with an address. In this case, no, stop. And call the command PC HL. So E9 is PCHL. He will set the program counter with the value of the register HL. Loading HL. HL is loaded with the address. Program counter is currently at 43. And PCHL, we set the program counter with the values of HL. Program counter is 3 and the hold command. And now the conditional jumps. The first one is JZ, which stands for jump on 0. So 0 flag is set, so we will jump. If I say here jump on non-0, 0 flag is set, it will only jump on non-0, so it will bypass the jump and halt the program. So you have the following conditional jump commands: jump on 0, jump on non-0, jump on carry, jump on non-carry, jump on parity odd, and jump on parity even, and jump on plus, and jump on minus. So what will happen here? A is loaded with 10, we are subtracting 10 from it, the result will be 0, and the 0 flag will be 1. 0 flag is 1, it will not jump, because it's jump on non-0. If you say here, we're doing a subtract here, from 11 and jump on minus. Subtract, the result will be negative, so the sign flag will be 1. Result is FF, sign flag is 1, and he will jump on minus, so he will jump to address 40. If you say on plus, he won't jump. Okay. If we're removing just 1, oh yeah, I want to do it example with carry flag. Again, removing 1, carry flag is 0, he won't jump. The easiest way, well, the problem here is we are modifying the accumulator, but if you want only to check if the value, a specific value is in the accumulator, you have the command compare immediate. So we will do the same as the sub command here, but with the exception, he won't put the result in the accumulator. He will leave the value intact in the accumulator, but he will change the flags. A is loaded with 10, comparing with 1, or compare it to 1. So internally we will do a subtract, result will be 9, so 0 flag will be 0, sign flag will be 0, and the carry flag will be 0, and so on. The result stays the same, carry flag is not set, so we will halt the program. A is loaded, we will subtract it internally, 10 minus 10 is 0, but he won't change the result here, but sets the flags appropriately. Stays 0, but the 0 flag is set. Same goes for here. 11, let's say jump on minus. Result stays the same. Yeah, I want to do it this way. Result stays the same. Sign flag is set because 10 minus 11 is a negative number, and so we will jump on minus. Let's do an example with jump parity even, parity odd. So exclusive OR with A will clear the accumulator and set parity to 1 because there are 0, 1 bits. That's even. So jump on even will jump to the address. And with 1, FFF and an AND with 1, the result will be 1. Parity is 0 because there's one bit set. So jump on parity odd will also jump to the address 40. Then next to the compare immediate, there's also a compare with a register. You can use register A, B, C, D, E, H, L, and also the memory M. So 1 minus 2 is FF, and FF, there are 8 1 bits, so the parity will be 1. So B is loaded, compare. So parity is 1, jump on parity odd, won't jump. Suppose you want to do a wait loop. Let's say jump on wait. You say decrement B. As long B is not 0, decrement it. Jump on non-zero, wait, and then you jump to stop. B is loaded, jumping to 40, decrementing B, it's non-zero, so it will jump back to 40, decrement it again, decrement it again, decrement it again. Now B is 0, 0 flag is set, jump on non-zero, won't do it, and will jump to the stop command. Suppose you want to call the wait function several times in the program. So here you have another code, and you want to call the wait again. So what would happen here? He will jump to wait, and here he will jump to stop. There's no difference if you call the jump here or the jump here. For that purpose, there's another command that's called call. Call, and here you won't do a jump to stop, but a return. Let me specify a stack pointer here at address F. So stack pointer is set at address F0. P is loaded with 5. Call is the address. He will jump to address 40, but before he will save the return address to the stack pointer. So the first call is here at address 5, and the next command would be at address 8. So he has to save the address 8 here to the stack pointer. He will first decrement stack pointer, F0, and input the address here. First the low byte, then the high byte, 0800. Program counter is at 5, stack pointer is at 40. Program counter is at 40, stack pointer is at address EE. At the address EE, he will find the return address, low byte, high byte. Decrement B is 0, 0 flag is set. The next command will be return. He will jump to the address 008. We'll set the program counter to the address 008 and increment the stack pointer. Increment 2 times because there are 2 bytes saved. Program counter is 8, stack pointer is back to F0, setting B to 1, calling program again. This time it's a second call. So the next address, so he has to put address D to the stack. Calling. So the return address is saved to the stack pointer, or to the stack. Stack pointer is the index here. Decrementing and returning back. And now the next command is halt. You can also call another subroutine. For example here, call dummy. Let's call it dummy, doing no operation, and return. Let me just exclude here the first call. So B is 1. Now A is put A. Oh yeah, I've changed the code, yeah. A is put as a stack pointer. And here we are calling again another subroutine. That's 48. So he has to put 49 to the stack pointer. Stack pointer is EE, so we'll decrement it to EC and put the next return address here. 4700. You can have a lot of nested subroutines as long as you don't overwrite your existing code. There's no problem with that. So returning back, stack pointer is incremented to EE. Another return, stack pointer is incremented to F0, and the program is finished. Suppose you want to do a 16-bit weight counter. For example, the value 30,000 decimal. How would you do that? So you have to change the subroutine here. Well, in that case, it would be decrement X, register B, that's BC. But if you remember right, the flags are not modified. Let's remove the dump here. We don't need it anymore. So BC is set, decrementing B is decremented. So the program stopped because the 0 flag was already set and the decrement X did not change the flag. So to B should be 0 and C should be 0. So you could say, for example, setting A to 0, comparing B, and then jump on 0 to something, and then comparing C and jump on 0. But that's a really bad code. So what you want to do is you move one register to A, to the accumulator, and you do an OR with the other register. Remember, OR, if at least one bit is set, it's 1. So if both are 0, the OR will be 0 and the 0 flag will be 1. Decremented, moving B to A, do an OR with C, so it's not 0, so it will decrement. After BC turned 0 and 0 flag went to 1, returned from the subroutine. So next to the call command, you have also the call on 0, call on non-zero, the call on plus, the call on minus, the call on carry, the call on non-carry, and the call on parity odd, and the call on parity even. So we will only do the call if the appropriate flag is set. And the same we have also, for the return, we have the return on 0, return on non-zero, return on carry, return on non-carry, return on plus, return on minus, return on parity odd, and return on parity even. So with the return z, he will only return if the z flag is 1. Beware when you use the parity odd and parity even in arithmetic, after arithmetic operations, the result will not be the same between an Intel 8080, 8085 or a Zilog Z80. The Z80 examples are in a separate video. Thank you for watching and see you in the next part. Bye bye.